Hello everyone and welcome to the OneClass channel. My name is Donna and I'm a recent master's graduate from the Material Science program from the University of Ontario Institute of Technology, also known as Ontario Tech University. So today we're going to go over some commonly asked questions in chemistry at the high school, college, and university level. So if you needed any help with homework or with tutoring, then check out the links in the description below. Now let's just get started on our set of questions for today's session. Okay, so question 1 says that most of the sodium chlorate produced in the United States is converted into chlorine dioxide, which is then used for bleaching wood pulp. Sodium chlorate plus 2 moles of hydrochloric acid makes chlorine dioxide plus chlorine gas plus sodium chloride plus water. How many milliliters of 12.1 mole per liter hydrochloric acid is necessary to react completely with 35.09 grams of sodium chlorate? Part B, what is the maximum mass in grams of chlorine dioxide that can be formed from the complete reaction of 65 milliliters of 12.1 mole per liter hydrochloric acid? Okay, so before we try to answer these questions, we first need to write down the balanced chemical equation, which thankfully was already written out for us. It's 1 mole of sodium chlorate plus 2 moles of hydrochloric acid produces 1 mole of chlorine dioxide plus half of Cl2 plus sodium chloride plus water. Okay, so managed to fit it all in one line. And now for part A, how many milliliters of 12.1 mole per liter HCl is necessary to react completely with 35.09 grams of sodium chlorate? So this is part A. And step 1 is to find the number of moles of sodium chlorate. So first let's calculate the molar mass of sodium chlorate. And we know that it's going to be the molar mass of sodium plus the molar mass of chlorine plus 3 times the molar mass of oxygen. Okay, so these are just values that you would find on your periodic table. For sodium, it's 22.99 grams per mole. Chlorine is 35.45 grams per mole. And finally, oxygen's is around 16 grams per mole. So now if we sum these all up, we get a final molar mass of 106.44 grams per mole. So now that we have the molar mass of sodium chlorate, we can calculate the number of moles. So recall that number of moles is equal to mass over molar mass. So the mass was given in the question. It's 35.09 grams. And the molar mass is what we just calculated. So 106.44 grams per mole. Okay, so now our grams will cancel out, and we're left with our units in moles, and you end up with 0.33 moles. Okay, so step 2 is to now find the number of moles of HCl by using molar ratios. So we know that we have 0.33 moles of sodium chlorate, and now we need to multiply by the molar ratio to find the number of moles of HCl. So we know that 2 moles of HCl are needed for every 1 mole of sodium chlorate. And we find the molar ratio by using our balanced equation. And notice that you know you did it correctly if your moles of sodium chlorate cancel out and you're left with the number of moles of HCl. So in this case, we get 0.7865 moles of HCl. So finally, for step 3, we need to find the volume. Find volume of HCl. So if we recall that the concentration is equal to number of moles divided by volume, then we can rearrange this equation to get volume is equal to number of moles divided by concentration. So we found the number of moles to be 0.7865, and the concentration is given in the question. It is 12.1 moles per liter. So now our moles will cancel out and we're left with our liters. So let me pull up a calculator. And you get 0.065 liters, which is the same as 65 milliliters. Okay, so 65 milliliters is needed. Oh, I just realized that I did my first part wrong. So 0.33 times 2 is actually 0.66. I think I was looking ahead, so let me just fix that. So that's just going to affect all of the remaining answers. But we still follow the same steps. And that's why it's always important to show all of your steps, because even if you mess up the calculations, if you show up all of the different steps, you still get part marks for your answer. So now we end up with 0.0545 liters, or 54.5 milliliters. Okay, so that makes more sense. And that was just for part A. So for part B, I'll do it on the next page. What is the maximum mass in grams of the chlorine dioxide that can be formed from the complete reaction of 65 milliliters of 12.1 moles per liter HCl. Okay, so this is a similar question as our previous one. So the first step is to find the number of moles of HCl. So again, concentration is equal to number of moles divided by volume. So to find number of moles, we just need to multiply concentration and volume. And let's convert our volume to liters because our concentration is in moles per liter. And we want the units to cancel out. So 65 milliliters is the same thing as 0.065 liters. Yep. And now our liters will cancel out, and we're left with our number of moles, which is, this is equal to now 0.787 moles. Okay, so for part 2, we now need to use the molar ratios to find the number of moles of chlorine dioxide. So we have 0.787 moles of HCl. And we need to look at our balanced chemical equation. And you'll see that for every 1 mole of chlorine dioxide that's formed, it needed 2 moles of hydrochloric acid. So then we can write out our molar ratio. So 1 mole of chlorine dioxide is formed with every 2 moles of HCl. So then we just divide this value by 2, and you end up with 0.393 moles of ClO2. So now step 3 is to find the mass of chlorine dioxide. And first we need to find out the molar mass of chlorine dioxide, which is just going to be the molar mass of chlorine plus 2 times the molar mass of oxygen. So the molar mass of chlorine and oxygen are just found on the periodic table, 35.45 for chlorine and around 16 for oxygen. And you end up with a molar mass of 67.45 grams per mole. And now we can calculate for the mass, because the mass is just equal to the number of moles times the molar mass. So the number of moles we found in the previous step was 0.393 moles. And the molar mass we just calculated to be 67, I'll just say 67.5 grams per mole. So it can all fit. And we get a final grams of 26.51. Okay, so now let's see what the junior tutor said, starting with part A. First, convert the mass of sodium chlorate to moles of HCl using their stoichiometric ratio given in the balanced equation. And they have the molecular weight of sodium chlorate to be 106.44. So they did it all in one step. They showed 35.09 divided by 106 to get 0.33. And then they multiplied this by 2 to get 0.66. And then they calculated for the volume by dividing number of moles by concentration and got around 55 milliliters. Okay, so now for part B, they found the number of moles of HCl, 0.787 moles, and then converted this to mass by using the stoichiometric ratio as given by the balanced equation. And they also got 26.5-ish. So this solution is correct. Okay, so question number 2 is what is the Lewis structure of NH2CH2, add lone pairs and multiple bonds, and then draw the valence bond picture of the sigma bonding framework. Okay, so first we need to find the Lewis structure of this compound. And the first step in finding the Lewis structure is to calculate the total number of valence electrons. In the case of nitrogen, nitrogen has 5 valence electrons. Carbon has 4. And we have 2 carbon atoms here, so we multiply this by 2. And hydrogen has 1 valence electron. And there are 5 hydrogens, so we multiply this by 5. And then if we add this up, we get a total of 18 valence electrons. So now let's start off by writing the Lewis structure. So we kind of get a hint of what it might look like because of the way the equation is written down. We have a nitrogen with 2 hydrogens bonded to a carbon with 1 hydrogen bonded to another carbon that has 2 hydrogens. Okay, so notice that both of the carbons don't have a full octet yet, and the easiest way to solve this is just to add a double bond in between the 2 carbons. And if we count out all the electrons I've drawn so far, each bond contains 2 bonding electrons. And we have 8 bonds, so we only have 16 electrons drawn so far. So for the remaining 2, I'm just going to add them as lone pairs on my nitrogen. So this is the final Lewis structure of our compound. And the second part of the question is to draw the valence bond picture of the sigma bonding framework. Okay, so I was never good at drawing these, but can be pretty simple because you just need to draw your atoms like so. Let me do the hydrogen in a different color. So we have 2 hydrogens, and we can show the sharing of electrons. Let me just draw this a bit more. Between the nitrogen and the 2 hydrogen atoms. Okay, so then we draw a bond like this. And we can also show hydrogens. just to show the sharing of electrons. And nitrogen has an extra lone pair. I'm just going to draw that over here. Like that. And notice that the bonds that are formed between nitrogen and hydrogen are sigma bonds. And we can see that it has head-on overlap. Overlap. Okay, so now let's try to do the same thing with our carbon. So I'll draw the two electrons shown in the middle that are being shared. And you can see another sigma bond is formed between the carbon and the nitrogen. And I can also show my hydrogen up here. And there's another sigma bond between the carbon and the hydrogen. And we have another carbon beside it. So let's do it in this purple color. And notice that there is a double bond. So when we have the formation of a double bond, there is still a sigma bond that connects the two carbons. So let me draw this in the same way we've been doing so. But now, both of these carbons have unhybridized p orbitals. I'm just going to show it as this long unhybridized p orbital like this. And this is shown on both of the carbons. And this is how the double bond is formed. So they're kind of connected like this. And we can label this bond as a pi bond. So this is when you have side by side overlap. Okay, and then just for the last carbon, it has two more hydrogens bonded to it as well. And then we just draw those two sigma bonds. Like so. Sorry if it's a bit messy, but this is the valence bond picture of the sigma bonding framework. So I'll just label this whole thing as the valence bond picture. Okay, so now let's see what the junior tutor said. Step 1 is to list the elements, their valence electrons. Just give me a second to count that out to make sure that we have a total of 18. Yeah. And determine the total valence electrons if the charge is present. Add the value of the charge to the total valence electrons when it is a negative. Subtract if it is positive. So they have 18 in total, and they got this skeletal structure of our compound, and they added the remaining electrons on our nitrogen because we have 18 valence electrons. Okay, so that's correct. And now the valence model is shown below. The sigma bonds are head-on overlap of orbitals and are represented by the overlapping shapes, while the pi bond, which is a side-to-side overlap of the p orbitals from both carbons, are presented by the dashed line. Okay, so they got the same structure. It's much more neat. So this solution is correct. Okay, so question number 3. When sulfur dioxide and nitrogen dioxide are mixed, the following equilibrium is set up. So we have NO2 gas plus SO2 forms NO plus SO3. And the Kc value is 1.44. In one experiment, 1.64 moles of nitrogen dioxide was mixed with 1.64 moles of sulfur dioxide in a 4-liter flask. Step 1 is to construct an ice chart for this equilibrium. Step 2, using your ice chart, calculate the concentration in moles per liter of sulfur dioxide in the flask at equilibrium. Submit your answer to part B, given your answer to 3 significant figures. Do not include units since they are already stated in the question. Okay. So I'm just going to first calculate the concentration on top here for both my nitrogen dioxide and sulfur dioxide. They have the same number of moles and the same volume. So we can just do 1.64 moles divided by 4 liters is equal to 0.41 moles per liter. Okay, so this is the concentration for both nitrogen dioxide and sulfur dioxide. So now let's construct our ice table. We know that the initial concentration of both of these was 0.41, and the initial concentration of both of our products would just be 0, since we don't have any products at the start of our reaction. So the change that occurs is negative X for both of our reactants, and the change for our products is positive X. So now when we write out the concentrations at equilibrium, we get 0.41 minus X for both of our reactants, and we just get X for both of our products. Okay, so this is the ice table, or the ice chart. And now let's write out our expression for Kc. So Kc is equal to the concentration of our products multiplied together divided by the concentration of our reactants. Okay, so now that we have an expression for Kc, we can plug in all the values that are given So we know Kc is equal to 1.44. And we know that the concentration of both of our products is equal to x. So x times x is just x squared. And the concentrations of our reactants are both 0.41 minus x. Okay, so now we just need to simplify this expression and solve for our unknown. So when we multiply the brackets like this, we multiply the first two, so 0.41 times 0.41, you get 0.1681. And then our inside term, so negative x times 0.41, and then the same outside term, 0.41 times negative x, you get 0.82. So it's that first, outside, inside, last that they teach you in math. And then for last, you multiply negative x times negative x, and you get positive x squared. So now we have this quadratic formula as our denominator. Then we just need to expand this some more. So bringing our denominator, multiplying everything by 1.44, you get 0.242 minus 1.18x plus 1.44 x squared is equal to x2. And finally, we just need to bring our x squared over to the other side by subtracting it. And you get 0.44 x squared is equal to 0. So now if we solve for x using a quadratic equation calculator or a quadratic equation, you just end up getting 0.224 equal to x. And now we can calculate the concentration of sulfur dioxide at equilibrium. So we know it's going to be equal to 0.41 minus x, and we found x to be 0.224. And you end up with a final concentration of 0.186 moles per liter. Okay, so now let's see what the junior tutor said. Step 1 is to compute for the initial concentrations of nitrogen dioxide and sulfur dioxide. So they got 0.41 for both. And they constructed their ice table, yep. And then they wrote out the expression of Kc. And also got x is equal to 0.224. So now when finding the sulfur dioxide's equilibrium concentration, they also got 0.186. So this solution is correct. Okay, so question number 4. What is the heat change when a 225 gram sample of olive oil, so they have the specific heat capacity given, is cooled from 95.8 degrees Celsius to 52.1 degrees Celsius. And then we have multiple choice. So we just need to find the heat change. So to do that, we use the equation Q is equal to mc delta T. So Q is the heat, and its units are typically in joules. M is the mass in grams. C is the specific heat capacity. And depending on the type of compound you have, they each have a specific heat capacity in the units joules over grams times degrees Celsius. And finally, delta T is the change in temperature. So delta T is equal to T final minus T initial. Okay, so now that we have our formula, we can just plug in everything that we know. So we're trying to solve for Q, and we're given the mass of olive oil, which is 225 grams. We know its specific heat capacity is 1.79 joules over grams times degrees Celsius. And we know its final temperature is 52.1 degrees Celsius, and its initial temperature was 95.8 degrees Celsius. Okay, so when doing this calculation, I would do the subtraction first in brackets, and then multiply it out, and you should end up with a negative value, negative 1.76 times 10 to the negative 4, and the units are in joules. So if we look at the options that are given, this is option C. Okay, so let's see what the junior tutor said. The heat change in energy is given by the equation Q equals mc delta T, where Q is the heat change, M is the mass of the substance in grams, and C is the specific heat of the substance, and delta T is the change in temperature. They got the same, negative 1.76 times 10 to the negative 4 joules. Yep. Sorry, I put a negative here. It should be just positive 4. So this solution is correct. Okay, so question number 5. What is the balanced net ionic equation for this reaction? So first, let's write out this full molecular equation that they gave us in the question. So it's already balanced as well, which is good. We have 2 moles of silver nitrate, aqueous, plus cobalt iodide, aqueous, produces 2 moles of silver iodide, solid, plus cobalt nitrate, aqueous. Okay, so this is the full molecular equation. So when we want to find the balanced net ionic equation, we first need to write down the total ionic equation for this reaction. So when writing out the ionic equation, this just means we separate everything that's in the aqueous phase into their respective ions. So basically, everything in this reaction will be in their ionic form, with the exception of the silver iodide, which is a solid. So if you have a pure solid, liquid, or gas, then it just stays in its same phase, but everything else will be written as the ions. So let's separate silver nitrate into its ions. You get 2 silver silver plus plus 2 nitrate yeah, 2 nitrate, which is NO3 minus. Oh, I'm also going to write in the forms just so that we're consistent. So these are all aqueous. Plus the cobalt iodide. So cobalt has an oxidation state of 2+, and we have 2 singly charged iodines. Okay, so these are all of our reactants, and then I'm just going to continue writing the products down here. So our precipitate stays the same. And then we just separate the cobalt nitrate into its ions. Like so. So this is our full ionic equation. And now when we want to find the net ionic equation, we need to cross out all of the spectator ions. So spectator ions appear the same on both the reactant side and the product side. So if we look at our example, we have 2 nitrate that appears on both sides, and we also have the cobalt ion that appears on both sides as well. So now when we write out our net ionic equation, it's going to be 2 silver plus aqueous plus 2 iodide makes 2 silver iodide solid. Okay, so now let's see what the junior tutor said, is to consider the following equation. It is a molecular equation for the formation of silver iodide precipitate, and its corresponding ionic equation is the following. Okay, so they wrote out all of the ions with the exception of the precipitate. And then from the equation above, it can be observed that the cobalt ion and the nitrate ion appear unchanged on both sides of the equation. This means that when the two solutions are mixed, neither the cobalt ion nor the nitrate ion precipitates in the reaction, hence they can be eliminated, and then they have the net ionic equation as 2 silver plus 2 iodine minus makes 2 silver iodide. The ion that does not participate or does not take part in the chemical reaction is called a spectator ion. From the equation above, the sodium ion and the nitrate ion are both spectator ions, hence they are eliminated in the net ionic equation. The net ionic equation is the chemical equation that shows only those elements, compounds, and ions that are directly involved in the chemical reaction. When writing the net ionic equation, the positively charged silver cation was written first on the reactant side, then followed by the negatively charged chloride ion, anion. Net ionic equations must be balanced by both mass and charge. Balancing by mass means making sure that there are equal numbers of each element. On the other hand, balancing by charge means making sure that the overall charge is the same on both sides of the equation. Yep, so you can see that for our example, we have two positively charged silver ions with two negatively charged iodine ions. And when you think about the sum of these charges, it's neutral, which is good because on our product side, we just have a neutral compound. So the solution is correct. Okay, so question number 6. Ethanol is the active ingredient of alcoholic beverages. It is also a possible replacement for gasoline. The complete combustion of ethanol forms carbon dioxide and water. Balance the equation, and what mass of carbon dioxide is formed by the complete combustion of 775 grams of ethanol? Okay, so let's write out ethanol. Reacts with oxygen to form carbon dioxide plus water. Okay, so now we need to balance this combustion reaction. And it's easy when you balance out your carbons first. So step 1 is to balance your carbon. So if we look at our reaction, you'll see that there are 2 carbons on our reactant side and only 1 on our product side. So we just need to put a coefficient of 2 in front of CO2. So now I like to balance my hydrogens next, because if I balanced my oxygens first, then you'll see that oxygen is both in CO2 and in water. So we only want to do it like once instead of having to redo all our coefficients. So that's why I balance hydrogens next. So we have 3, 4, 5, 6 hydrogens on our reactant side and only 2 on our product side. So we just need to put a coefficient of 3 in front of H2O. So now that both of my carbons and hydrogens are balanced, we can finally balance oxygen. So on our product side, we have a total of 7 oxygens. And on our reactant side, we only have 3. So the easiest way to have 7 oxygens here is to just add a 3 in front of O2. So now we have our balanced equation. So now let's try to answer the next part of the question. What mass of carbon dioxide is formed by the complete combustion of 775 grams of ethanol? So let's write down everything we know. We know the mass of ethanol is 775 grams. And we also need to calculate the molar mass of ethanol as well. So I'm going to denote ethanol as ETOH. And its molar mass is equal to 2 times the molar mass of carbon plus 6 times the molar mass of hydrogen plus the molar mass of oxygen. So if we look at our periodic table, we'll see the molar mass of carbon is 12.01 grams per mole. And the molar mass of hydrogen is 1.01 grams per mole. And the molar mass of oxygen is 15.99 grams per mole. So now, if we add all of these values up, we get a total molar mass of ethanol equal to 46.07 grams per mole. Okay, so we are looking for the mass of carbon dioxide. So let me do this in a different color. Mass of CO2 is equal to grams. And we can also find the molar mass of CO2 just by using the same method we did earlier. So 12.01 plus 2 times 15.99 gives us a molar mass of 44.01 grams per mole. Okay, so this is everything that we are given in the question. And now step 1 is to find the number of moles of ethanol. So we do that by using the equation number of moles is equal to mass over molar mass. So the mass of ethanol was 775 grams, and the molar mass we calculated to be 46.07 grams per mole. So now if we just divide the two, we end up with 16.82 moles of ethanol. Okay, so step 2 is to use the mole ratio to find the number of moles of carbon dioxide. So we know that we have 16.82 moles of ethanol. And then by looking at our balanced equation, we can find out the mole ratio we need to find the number of moles of CO2. So we know that 2 moles of CO2 is formed for every 1 mole of ethanol. And we can double check that we did the molar ratio correctly if you see that the moles of ETOH cancel out, and we're left with the number of moles of CO2. And when you multiply 16.82 by 2, you get 33.64 moles. And this is of CO2. So finally, we can now do step 3, which is to find the mass of CO2. So we know that the mass can be found by multiplying the number of moles times the molar mass. So we found the number of moles in the previous step, which was 33.64 moles of CO2. And we also know the molar mass of CO2, which is 44.01 grams per mole. So now if we multiply these values, we end up with 1,479.82 grams. Or we can write this in kilograms. So just by dividing by 1,000, you get 1.48 kilograms. Okay, so now let's see what the junior tutor said. A balanced reaction refers to a chemical reaction wherein the number of atoms both present, wherein the number of atoms both present in the reactants and products are equal. So they summed up how many of each atom were on both the reactants and the product side, and they showed it step by step and found the balanced chemical equation to be the following, which is what I have as well. So they balanced it correctly. And now they want to convert the mass of ethanol to the mass of carbon dioxide using the stoichiometric ratios given in the balanced equation. So they have the molar masses for both. And they did it in one step. So first you find the mass of CO2 is equal to the moles. Yep, so then they showed how you would calculate number of moles, mass over molar mass. And they got 16.82 moles of ethanol. And then they used the mole ratio and then multiplied by molar mass to get a final mass of 1,481 grams or 1.481 kilograms. Okay, so this solution is correct. Okay, so question number 7. Sodium carbonate and nitric acid total ionic equation. I'm guessing they just want us to find the total ionic equation if we have sodium carbonate and nitric acid reacted together. So first, sodium carbonate. Sodium has a +1 charge, and the carbonate ion has a 2- charge. So then we need 2 sodiums to react with our carbonate to get a neutral compound. So this is sodium carbonate, and it reacts with nitric acid, and its formula is just HNO3. So when this reacts, you get sodium nitrate plus water plus carbon dioxide. Okay, so when we need to balance this equation, we have 2 sodiums on our reactant side, so let's put a 2 in front of sodium nitrate. And now we have 2 nitrate ions, so we just need to add a 2 in front of nitric acid. And now if we look at both sides of the equation, everything should be balanced. Okay. So now we just need to write out the ionic equation. And pretty much everything that is in its aqueous form will be separated into its ions. So when sodium carbonate is separated into its ions, we get 2 sodium plus ions. And 1 carbonate ion that has a 2- charge. And with nitric acid, we get 2 protons and 2 nitrate ions. And for our products, we get 2 sodium ions and 2 nitrate ions. And then our water and our carbon dioxide remain the same, since they aren't in their aqueous form. Okay, so this is the ionic equation, and now we need to write out the net ionic equation. So the net ionic equation, it doesn't contain any spectator ions. So spectator ions are found on both the reactants and the product side. So in our case, 2 sodium ions are on both sides, and the 2 nitrate ions are on both sides. So our net ionic equation is just the carbonate ion plus 2 protons produces water plus carbon dioxide. Okay, so now let's see what the junior tutor said. Step 1 is to write the unbalanced equation, indicate the states of the substances involved, and then they balanced out the equation. Yep. And now we write the complete ionic equation, write all aqueous substances in terms of their ions. So that is correct. And then write the net ionic equation, canceling out the spectator ions or the ions both present in the reactant side and the product side. Okay, so this solution is correct. Okay, so those are all the questions for today's session. And if you enjoyed today's Q&A and you'd like to be notified of when we do this next, please hit the subscribe button and notification bell below. If you'd like to submit a question of your own, then check out the links in the description. And also, if you enjoyed today's video, you can give it a like and a comment, or you can share it with your friends and classmates if they needed any help with chemistry. This has been Donna from OneClass, and I hope to see you soon. Bye.